please sit down, then we can start. I think most people know Ramon Hanssen. He's our Dutch professor in INSAT, more or less. So he asked for 5 minutes extra and we granted him. Because the last presentation will not be there. We had problems with visa, etc. So that's why we can do this. Please, go on.
Thank you very much, Jan. Yeah, thank you for being here. Actually, you may not know it, but you're on sacred ground here. This particular room is the place where in TU Delft every PhD student defends his PhD thesis. So this is the place where, if you're doing a PhD here, you hope to end up here behind that place, because then in the end you may get your PhD. And the Dutch PhD is particularly special because you don't need to only write a thesis, but you also need to come up with propositions, or stellingen as we call it in Dutch. And propositions is basically a list of statements, usually one sentence. And these are formulated in a way that they should be opposable by the opposition of the PhD defense. And this is a very interesting part of the defense. Usually there are also questions about the propositions. So what I decided to do today is to come up with propositions, right? I'm coming up with 3 propositions, and the title here is Land Subsidence Monitoring in the Netherlands. A bit broad picture, but I thought to share 3 lessons with you that I think may be valuable to you. Maybe some of the things are very well known to you, but I found them valuable. So here are my 3 propositions. Proposition number 1 is subsidence is in the eye of the beholder. Right, so if we're looking at this beautiful bunch of flowers over here, everybody among you may decide whether this is beautiful or not. And although we are talking about subsidence also as something that is kind of factual or something that we cannot have any doubt about, I think it is in the eye of the beholder. It depends on who's watching. The second proposition is that we should talk more about Euler and Lagrange. And this is something I think that this audience doesn't speak enough about, and I hope to convince you of that proposition. And finally, although we are looking at satellites and radars in space, we definitely still need geodetic ground infrastructure, similar like Alessandro also indicated in his talk. So these are the 3 propositions, and I will go over them one by one. So subsidence is in the eye of the beholder. So first of all, the first word, subsidence, is not necessarily something that is very well defined, right? So what is subsidence? What does it mean for somebody who is interested in it? And these 4 pictures here give an example of that. On the upper left, you see a picture of a little girl who needs to step outside of her door, but the ground in front of her door has subsided quite a lot. So the house is not subsided, but the ground is subsided. If we get a measurement from the house, we will not see subsidence. If we get a measurement from this ground next to it, maybe 1 meter further horizontally, we see subsidence. On the upper right, you see also subsidence, but very small, right? Very localized. And so this is something that may not interest many of you here in the audience, but if you're in a wheelchair and you need to go here, this is very important to you. And it's also subsidence, right? There is no length scale. Lower left, you see a house on the right-hand side there that is subsiding a lot, really a lot. I just drove by that house last Sunday, and I'm amazed that still people live in there. That particular house is subsiding, the house next to it is not, the street next to it is also not subsiding. So what are we talking about if we're making subsidence maps, right? This is in the eye of the beholder in a way. Now, if you look at our developments in making maps using INSAR, because that is the thing that I worked on, we had quite a bit of a history, and I would like to take you through it in the Netherlands. So ground motion in the Netherlands in 4 episodes. Episode 1 is 2010, when we made the first ground motion map of the whole country. And we made a decision here. You can see that here in the blocks on the right-hand side, we made a decision to only have high resolution where we really need it. And that means that we had less measurements and a little bit more noise. In the locations where we don't have that much motion, we average more, and that means that we can decrease the noise level. That's a decision. You can make that. You can also decide not to make it. We made that decision. On the left-hand side, you see that we also combine this with leveling, with GPS, and also with absolute gravity measurements that we're doing at those locations. So this was basically the first product. Then 2018, there was another map. It looks about the same, right? We still see the Groningen field going down, but there is a lot of stuff on the left-hand side here. And here we decided to do something different. We decided to make a difference between the deep causes and the shallow causes. And if you do that, then you would see here only the deep causes, and here you would see only the shallow causes. Now, the way how to do that, that is a whole story in itself, and I'm not claiming that this is the only way to do it. You can, if you make different decisions, you get different maps. But this was episode number 2. Then we had episode number 3. That was the map that we made in 2020, where similar to the European ground motion map, we had the point level. You could really zoom in to your own house, and you could see much more detail. So that, again, was a different perspective. We didn't do the deep and shallow decomposition or the subdivision, but we just showed what we had. Then 2 years later, Alessandro already presented it. We now have the whole deformation map of Europe, right? So you can now go to your computer and log in and zoom in to all these points and point level in Europe. And the final one is now the one that is the Benelux. I think it's not yet online yet, but this is the latest version, which goes until the end of 2022. Now, lots of maps, lots of points, lots of data. Yeah, you can download this all, you can play around with it. But what good is it? So now if you compare, for example, this last Benelux map and the European ground motion map that is here on the screen for the aula, the building in which we are now, on the left-hand side, you see that. Then, okay, so what do you see? You see green dots, orange dot, yellow dots, and you know which one are you going to use, right? You can download both if you like. So the main question is, when are we happy, right? And I'll give you just 2 seconds to think about the answer to that question yourself, right? When are we happy? Which one would you like to have? Okay, I'll give you my answer. It depends on the application. Right? It depends on what you want to do with it. And this is not a kind of cheap trick or so, but this is really a very fundamental thing in INSAR. So what can we learn from this? What I try to do is to ask myself the question, what if we would make a dictionary and we would put the word INSAR in the dictionary? What should we write in that dictionary? And this is what I came up with. So INSAR would be a family of techniques using synthetic aperture radar interferometry to provide displacement estimates by advanced data processing, something like that, right? And the key thing that I would like to bring here is this family of techniques. So INSAR is not one thing, it is a family of techniques, a family of data processing methods that you can use to get displacement estimates. So if you would agree with this definition, and I invite you, this is a proposition, so I hope that I get resistance also here, but if you would agree with it, there are a couple of consequences. First consequence is that with INSAR, we can make an infinite number of products. If we have the same data, and I would give the same data to Alessandro or to Urs or to anybody else here in the audience who has the data processing software, you can make different products and they will look different, right? So we're not going to end up with the same product. That's the first consequence of this definition. Second one, if you want to decide which product is optimal, that depends per definition on the application that you're applying, right? This is the consequence of this definition. And if you would agree with that, then if you need to know the application, then the intended application needs to be known beforehand. So if we are starting to make maps of the Netherlands or of Europe, of which country, and we don't know what the application is, we run into trouble. So basically my statement is that without an intended application beforehand defined, we will always get suboptimal results. So in other words, we can always produce something better if we do know what a product is going to be used for. So this is, for me, a very important lesson. And so this is my argumentation for this first proposition. Subsidence is in the eye of the beholder. Depends who's using it and which kind of problem you want to solve. Proposition number 2, we should talk more about Euler and Lagrange. And this is a very interesting one, which came up to some recent work that we did with Wietske Brouwer here. And so Euler and Lagrange, the names sound familiar probably, both 18th century scientists. And if you look at fluid dynamics, which is a very interesting branch of science, you see that subsidence relates a lot to fluid dynamics. So basically Euler's approach states that we're looking at elevation at fixed positions. Lagrange approach is that we are following particles. And let me explain the difference between those two approaches. So the Eulerian description here on the left-hand side would mean that we simply have vertical motion at a certain point, that we get a deformation, we get a subsidence bull. And the main question that belongs to the Euler description is how does the elevation change for one particular horizontal coordinate? Now you can talk about Euler and then define, okay, do we have Eulerian geodetic techniques and do we have Eulerian models? And yes, we do. We have Eulerian geodetic techniques. Leveling, most important one. Airborne laser scanning or LiDAR, it's an Eulerian technique. If we look at the models, all the shallow subsidence models that we're currently using are usually Eulerian in their approach. And many of the kinematic deformation models, if we decide to fit a polynomial or so through the data, it's Eulerian. So basically, we're having a geometry-driven approach here. Now let's go to Lagrange. So what does Lagrange say? Lagrange has points which are also on the surface. And we have some kind of source, for example, here the light blue dot. And basically, the source is driving the mechanism. So basically, we also have a subsidence bull. And now we have deformations along the red arrows that you see over here. Now, these red arrows obviously also deform in the horizontal direction, right? So if you would compare that with the blue ones on the left-hand side, you see that there's a difference, right? Now, this is a Lagrangian, and the Lagrangian question is, where does a particle move between T1 and T2, right? So what is the motion of a particle? We're following a particle. It's just like we were putting a balloon in the air and try to follow where it is. So this is physics-driven. Now, Lagrangian geodetic techniques are INSAR and GNSS, because there we're following particularly a point, right? It's a totally different ballpark. It's a totally different ball game. In terms of techniques, if we look at finite element models or Mogi sources or the Hirschman models that we're using in the gas production, in the reservoir engineering, these are Lagrangian techniques. So the main message here is that these two descriptions are fundamentally different, right? They're incomparable. It's like soccer and hockey, right? So different things. And we should talk about that much more. It's even a little bit more complicated than the picture that I just showed you. Here you see another animation. So here again, we have the vertical displacements. Here we have then the motion, the figure that comes from that. But now if we include the horizontal deformation, we do not end up with the same subsidence bull. Basically, the horizontal deformations are over here. And the thick black line here, this is the subsidence bull that would be driven by a Lagrangian approach, physics-based. This is what a particle really does. There would be a tree on one of those lines on the top. It would move according to a certain pattern. So these surfaces are not the same. So now we can say, okay, this is all very small, just millimeters, and we can ignore that. But it's not. Actually, it's quite significant. And of course, this depends on the case that you're interested in. But my point here for this proposition is that we, as a community, should start talking about Euler and Lagrange, because it's very important to what we do. There's another interesting thing, that is, how does that particle move? So we also in the INSAR community, we talk about vertical deformation, horizontal deformation. But a particle doesn't move. Even if we look at this vertical part, basically what the particle does is this motion here, right? So this is a hyperbolic system, right? So here we have hyperbolic patterns, and this is the real pattern where a point moves. So we cannot simply ignore this and say we're only looking at the vertical deformation, because if you would look at point number P8 here and draw the vertical line down, you end up at a different curve, right? It's simply the wrong position. Now, combining all that and putting all this together, we can look at the two differences between the Eulerian and the Lagrangian approach. It has consequences for the tilt. So here, the Lagrangian and the Eulerian tilt they're given in blue. You see that they're different. It has differences for the curvature. Lagrangian and Eulerian are different. And most dominantly, it's very different for the strain, right? The strain, how much compression or extension do we have? Because in an Eulerian way, the light blue curve, every little segment would be elongated, would be getting longer, there would nothing be getting shorter. But in reality, we have extension and compression in these kind of curves, right? So basically, it's simply wrong if you would look at Eulerian strain. So the take-home message for the second proposition, Euler and Lagrange are fundamentally different. The impact, of course, is case study dependent. You can say if we have a very small motion, I can simply ignore it. Well, that's your choice. But I think the main point for us as a community is that we need to acknowledge that it's different. Strain is substantially different. Euler is simply wrong, right? It would only result in extension. Field and curvature are different. And also very importantly, we say, okay, we need to validate the INSAR result, so we use leveling. There we have a problem, right? These are two different things. This is, again, like soccer and hockey. There are different things. You cannot simply validate one with the other if you're looking at different types of motion. So, second proposition, we should talk more about Euler and Lagrange, and I hope that this week, maybe tomorrow, if you're on the excursion, you're sitting next to somebody in the bus, talk about Euler and Lagrange, because it's really fun. Proposition number 3, the last one, we still need geodetic infrastructure. Of course, there's this tendency to see, okay, let's try not to have a lot of stuff on the ground because it's expensive, it will break, it's a lot of hassle. Let's do things from space, but we need ground infrastructure. To make this point, I would like to quote a very famous Dutch scientist who lived just a couple of kilometers over here in Hofwijk, called Christian Huygens. And he wrote in Latin, as I did at last time, the sentences that are above here. I put it there in Latin also, if you're fluent in Latin, but I also put it in English. What he wrote is, whether objects are in rest or in motion cannot be determined unless it is with respect to each other. And this may sound very familiar to Newton's first law, right? Where Newton related this whole concept to forces. So whether if we need a force for something to change in velocity, we cannot say whether a point is in rest or in continuous motion. But I think Huygens, which was a little bit earlier, made a very more fundamental point. It simply said it was not observable. So from a philosophical point of view and also from a practical point of view, this is a tremendous discovery here. So we cannot simply say whether a point is in rest or in motion, because we cannot measure it. It's not observable unless it is with respect to each other. Now, what does that mean for us? So here I took an old picture that I got from Ginny Ketelaar when she was doing her PhD here a long time ago, but it still serves my purpose. Here we see the Groningen again. You've seen it several times. You see the color scale here. Well, this could be the color scale. This could be the color scale. This could be the color scale. You tell me. I don't know, right? We don't know which point is stable, whether the rest of the country is coming up or whether Groningen is going down. We simply cannot tell. It's not in our data. So what can we do about that? So we have three things that we're testing at the moment in the Netherlands. One is the integrated geodetic reference systems, the stations that I will talk about, collocated transponders, and free-floating transponders. So the first one is basically connected to the idea that if we have all these different techniques, and if we want to do something, if we want to compare data with each other, then at least we should know that we're looking at the same physical thing. And why that is important, I can show you in the next slide here. This is an area close to Amsterdam called Diemen, and you see the same area. It's the same data, actually. The only difference between the left-hand and the right-hand side is that the left-hand side are reflections from the rooftops of buildings. Everything is green, nothing is moving. On the right-hand side, you see all red points, which is the street next to those buildings, which is subsiding like crazy. And that is the difference between the double bounces that we have via the ground and going back to the satellite, and the direct reflections from the rooftop. So if somebody would say, well, we have a GPS receiver and it's very close, it's only 10 meters apart from my scatterer, it's a no-go, right? It's not comparable. You need to have really the same physical thing. And this is why we invented these geodetic reference stations. So we can have GNSS on there, we have INSAR, ascending and descending, all the different sensors. We have leveling, airborne laser scanning or LiDAR would measure the top of this plate. We have photogrammetry, tachymetry, relative gravimetry, absolute gravimetry, everything on the same physical station. So we're setting this out now. So in relation to the gas extraction, we started in the north of the Netherlands there, where there are about 30 of them. Some of them are taken away at the moment, but there still is a very dense network. Then we have about 5 here in the western part. There is one in Alveen in the middle. There will be one new one, hopefully, in the University of Twente area. And then also in Belgium, they're now placing several of them. I think Ateve had also a poster here for the one which is close to Antwerp. This is probably, in my view, our best one, because this is a station that we built on top of a bunker which has a foundation in either the Carboniferous or the Devonian. I'm not really sure which are the two, but it could be that the lower part of the bunker is really in the Devonian. So that is the lowest bedrock basically that we can have. It's a seismic station of KNMI, and every year we're doing absolute gravity measurements there. And last year we installed this here with our students, and so this is the station that is now basically, in my view, our best geodetic reference station that we have here, just because of the fact that it has such a good and a strong foundation. And if we use these stations, we can get up to, let's say, 0.3 millimeter precision if you look at the phase measurements in itself. What do we do with that? So if we have that whole network, what is the purpose? That is a question that you need to answer. And one thing is that if we have those, we can make a connection. We call this stepping stones, going from one point to another. For those of you who are going to the excursion to Zegveld tomorrow, this is a picture of Zegveld. And what you see here with the right red line, that is the IGRS station. It's one scatterer. And around it, we have point scatterers from buildings. And we're interested, like Phil showed this afternoon, we're interested in the fields, the green, the part where we don't have these nice colored dots. So basically the idea is you have these IGRS stations, you make connections with point scatterers around with it, you make a network, you do proper geodetic testing, and then from those points you move to the fields and all the parcels where you would like to see the real deformation. Now, if we do that, and Phil has explained that this morning, you get these kind of pictures over here where we have the motion of a single parcel or a group of parcels, really the grassland, so to say, but connected to an IGRS station, connected to GPS, where we have a very long and a stable time series. Then the second one are the free-floating transponders. Because we have these soft soils, we know that they react very strongly, and our well-founded IGRS will not see that because it has a firm foundation. Now, here are these, we call this FFTs, or free-floating transponders. They move with the ground. If the ground goes up, the transponder goes up. So we have installed several one of them. So this is the one in Zegveld that some of you will see tomorrow. There was one installed in Nieuwolda where Cheyenne showed the picture here. This is when it was installed and when they got some media attention. And for all those stations, we can then see how they move. And this is a result from Simon van Diepen, where he combined all the different tracks that we have over one particular transponder. And you see in the dashed line the ground truth measured from an extensometer on the ground. This is really the truth. And the colored dots are the two ascending and two descending tracks. So really, in this case, we can follow the motion very well. And I would like to particularly draw your attention to the scales here. So this line starts at 0 and it goes down to about -7. So that is 7 centimeters of motion. It's this much over the period of, in this case, less than a year, right? So it's an enormous amount of motion, much more than the phase unwrapping problems that we have in INSAR. So without, let's say, a proper data processing technique and without a proper reference, you would not be able to do that. So then finally, the collocated transponders. This is the third category. Here we decided to put transponders on tide gauges. So these are locations, again, where we have GPS, where we have a tide gauge to measure sea level variation. We also have leveling benchmarks there, obviously. And this serves the same purpose. If we have such a station over here, we can go from there, connect it to all the other points. And that means that, so if you go one back here, this would be the situation before the correction. And this would be the situation after the correction if we have the one transponder which is connected to the GNSS antenna. So this is the end of my talk. I had 3 propositions. Subsidence is in the eye of the beholder. I think something very interesting, also interesting to discuss among each other. So is there the true subsidence? What are we using as definition? Or do we first need to make a definition before we make a map? That would be my argumentation. Second one is we should talk more about Euler and Lagrange because it's important. We don't see it that much in the literature related to subsidence, and I think we should. And finally, also for other countries in the world, it's great that we have the satellites, but we still also need ground infrastructure, geodetic ground infrastructure. And if we do that in a smart way, we can connect all the data sets together. Thank you very much.
Thank you. And now, are there questions?
Yeah, very nice talk. I just add a comment. I like your third proposal preposition, the third one. Yeah, we do need the geodetic infrastructure. I would emphasize that the infrastructure doesn't just mean the hardware, GPS stations or satellites. In fact, for our precise monitoring for long term, we need a stable regional reference frame. It's not a global reference frame. So we use long-term observations, establish regional stable local reference frame. Do you have, I believe you have, do you have a stable regional reference frame in this area?
Well, I would like to give you a different answer to that question because I don't fully agree that we necessarily need a stable reference. We don't need it necessarily. We need to know a point where we know the motion, right? So basically, with these IGRS, we're combining the two effects. So first of all, we would like to have it stable. That is why we give it a Pleistocene connection. But even if we wouldn't have that, we have the GNSS, right? And the GNSS gives us the motion in the global geodetic reference system, right? And that, because if we would only rely on some stability, that means that I, as a geodesist, have to listen to a geologist who tells me this is stable, right? And if I like to work with error bars, and if I just need to do some hand waving, well, you know, this point is probably stable, I cannot work with error bars anymore. Right? So this is why we have the two-way effect, so preferably stable. So we listen to the geologist and the geophysicist who tell us, okay, this is probably a good spot, great. But even if they're wrong, we still want to monitor the motion of that particular object. Yep.
More questions?
I just thought I'd add a little bit more to the discussion about Euler and Lagrange, because I work in a subsiding basin that has a lot of sedimentation. So the ground surface is not necessarily going down, even though there's a lot of subsidence.
Yeah, that's a great remark, because, for example, if you do laser scanning, and this is why laser scanning is an Eulerian technique. So if we put a bench of sand somewhere, right, and we do laser scanning before and after, the ground is going up, right? But it's not really upward motion, right? So, and if I dig a hole, the ground is not subsiding, there's a hole, right? Laser scanning would not see it, would not be able to distinguish whether that is a gradual motion or not. So this is exactly why it is so important to make the distinction between Eulerian approaches and Lagrangian approaches. Yeah. Yeah.
Thank you very much. Thank you very much for the very stimulating and nice talk. I fully agree with your second proposition. We should talk more about Euler and Lagrange, but I don't agree about the way you explained it. Good. In the sense that, as far as I understand, the way you put it, it seems that with the Euler approach, you basically neglect the horizontal displacement, while you take into account the horizontal displacement with the Lagrangian approach. But actually, using Euler or Lagrangian approach means changing your point of view, changing your reference frames. If you neglect the horizontal displacement with an Euler approach, you're just making a mistake. You're not using an Euler approach. And the second point, finite elements are not Lagrangian necessarily. They basically solve differential equations. So if you write your differential equations in Eulerian framework, then they are in a Eulerian framework. And when you use land subsidence models, typically you use an Euler approach also for with finite elements.
Yeah.
Thank you.
That second point, I'm glad you take it up. I think the first point, indeed, I would like to engage in the discussion because so if we, if in an Eulerian sense, right? So even if there is horizontal motion, but I'm just going to sample my certain latitude and longitude coordinate at 2 points in time, I get two values, right? So, but it is, so first of all, I would know, it's not just ignoring the horizontal motion, but I get like a different point on Earth. If there's a tree here and the tree moves like this, and I'm going to measure here at time t2, the tree is gone, right? So there's no tree anymore, right? So I think we should engage this discussion a bit further. Yeah.
Okay.
Okay.
Yeah, then you go to, no, sorry, last question, because when he starts about Euler and like, okay, let's go to Andreas Hermann.